Hello and welcome to everyone joining us. I am very excited about today's presentation and our webinar here. It's titled Bourbon, Brews, and UFOs, Identifying Unknown Materials in the Food and Beverage Industry using FTIR microspectroscopy. I'm a bit of a spectroscopy nerd myself, so this one really does get me fired up. So I'm Brian DeVerse. I'm your moderator here I'm the spectroscopy product manager at Quantum Analytics. And for those of you who are attending your very first quantum analytics webinar and are unfamiliar with who we are, Dave, if you could put on the next slide. So quantum analytics, it's a value-added distributor of multi-vendor analytical instruments, everything from chromatography, mass spec, to spectroscopy, to even some sample preparation instrumentation, and much more. We have been doing business for more than 30 years now. We are headquartered in Foster City, California, and we have a technical center in Houston, Texas, which is where I'm calling in from. Next slide. Our key to success is our ability to provide rental, leasing, and financing programs for companies ranging from startup labs to Fortune 500 companies. We provide cross-platform system integration, installation, training, application development, and product support. We maintain a multi-million-dollar inventory of new and refurbished instrumentation that's available for immediate delivery. As for me, I've been working in spectroscopy for more than about 20 years or so, and working in as customer support, doing technical sales, and even some application roles, from instrumentation ranging from X-ray, infrared, and near-infrared spectroscopy, Raman, and even some NMR. After all these years, I'm still very much a student of these technologies, and I learn more and more every time I get to work with one of you and have the pleasure to get involved in your applications. Next slide, please. I'm delighted to introduce today's speakers. So today we'll start with Dr. David Shearing, founder and principal at Czitek. Czitek is a small company dedicated to the development and marketing of vibrational spectroscopy products. Dr. Shearing has more than 30 years of experience in the business of instrumentation for chemical measurements and has been a titan in the development of groundbreaking vibrational spectroscopy technologies. I'd also like to introduce Dr. Gary Spedding, owner of Brewing and Distilling Analytical Services. Dr. Spedding started out as a biochemist, but has morphed into brewing and distilling analytical chemistry roles through his role as head of laboratory services at Sable Institute of Technology. He maintains a special interest in the origins and development of beverage flavor and in the sensory evaluation of beer and distilled spirits. He owns and operates Brewing and Distilling Analytical Services and the new division, Brewing and Distilling Educational Services, located in Lexington, Kentucky. And in the fall, he's excited to announce the second facility that will be in operation for BDAS in Denver, Colorado. Today, Dr. Shearing and Dr. Spedding will provide an overview of sampling and identification techniques used to solve contamination issues in the beverage and spirits industry. I would like to point out, although the main topic relates to the spirits industry, the technique can be applied to the food and beverage industry as a whole. So just before I hand over to our speakers, I'd like to mention just a couple of quick things. Please feel free to ask any questions for the Q&A session at any time during the webinar by clicking on the Ask a Question button on the side panel. Also, the on-demand link for the webinar will be provided a few days later. So without further delay, I'd like to hand this over to our presenters, Dave and Gary, and I would like to thank them for presenting to us today.
Thank you very much, Brian. This is Dave Shearing. And first, I'd like to give an overview of what we're going to be talking about today in the webinar, and thank all of our attendees for their interest in hearing what we have to say. And thank you for Gary and Quantum Analytics for providing the platform for us to speak to you today. So first, we'll give a little bit of an overview of contaminants in the food and beverage industry and how these can be a problem relative to poor product quality and the cost of poor quality in spirit and beverage products. We'll also talk about brewery and distilleries industry's challenges, some of the technical solutions that are available for quality problems that crop up in the food and beverage industry. We'll give an introduction to FTIR spectroscopy and microspectroscopy, and a specific description of the SurveyIR microanalysis accessory, which was used to solve the example problems that we'll be presenting today, specifically contaminants in brews and spirits. And then finally, we'll follow up with some final thoughts and questions and answers. So the food and beverage industry, the success of the business is really controlled by consumers and their perception of the product. Despite the manufacturer's best efforts, contamination of products are fairly common. And these contaminants can cause adverse effects that can be manifested in production downtime, the inability to ship product due to contamination, or if these contaminants are get into the hands of consumers, can provide a negative perception impact on the product. Both of these issues, of course, are costly to the company and can be described as the cost of poor quality. Recalls can happen, and consumers' response to them can be detrimental. And then in our modern society, social media platforms can help spread this negative information very quickly. And we've on the slide, we've indicated some recent issues that have cropped up in the media, which include cellulose particles found in from wood pulp that are found in Parmesan cheese, plastic material found in salt, and the most common issue that we hear about are bacteria outbreaks in the food chain. So this is just an example of what the cost of poor quality can be. And if we had a small business that generated around $500,000 in yearly revenue, which it breaks down to be about $1,370 per day, if a contamination issue shuts down the process line 6 times a year, and it's shut down for 3 days, each occurrence, each incident would cost about $4,000 just in lost product revenue. That doesn't include your costs, your fixed costs, which continue to accrue. So this would be about $24,000 a year just in lost shipments, and that would assume that these issues were resolved completely internally. If you have to go to an outside laboratory, your cost of resolving the issues would get higher to the tune of around $45,000 based on these six occurrences per year. And as an example of the cost of poor quality, in 2013, Tyson recalled over 10 tons of beef patties due to microplastics contamination in the beef. So what are some of the common food contaminants? The ones that get the most attention in the news, of course, are the bacterial infestations, which include Salmonella, E. coli, and others. Trace pesticides can be found on food products. And then we have particulate contamination, plastics, biological organisms like insects, fibers or hairs, and packaging materials. The technology that we'll be describing today can handle all of the issues from plastics through packaging materials. We cannot observe trace contamination due to pesticides at relevant concentration levels using infrared spectroscopy. And then because of the complexity of the biological matrix, we cannot differentiate a bacterial infestation from the food itself. So we can bacteria do have observable infrared signals, but the infrared signals we observe are very much like the proteins and carbohydrates and fats that make up the food product. What about beverages? Unlike many food items, beverages are commonly stored in transparent containers, so contaminants, particularly particulate contaminants, can be observed readily. The human eye can detect particles of dimensions in the 50 to 100 micrometer size range. That's the minimum size, which leaves these contaminants in plain sight. In some cases, visible contaminants are actually small pieces of the raw materials that are naturally in the beverage or are used in the production of the beverage. And there are some teas and unfiltered wine and beer which have particulate material, but it is intended to be so. The brewing and distilled spirits industry is challenged with visible contamination in the form of hazes and unidentified floating objects, which Dr. Spedding has termed UFOs. So large producers, large companies, and established companies over a period of time have been able to, on their own, sort out many of these haze issues and UFO issues. But there are a lot of smaller companies and microbreweries, microdistilleries, smaller companies that are on the growth curve of this industry that are left searching for answers. Spirits, contamination in spirits are more difficult to address than in beer, and this is because there's less data and research published on spirits. Older distilleries have acquired knowledge over time and have perfected their recipes and processes over the years. However, new distilleries face many challenges, and these distilleries are kind of on the leading edge of product creation, creating new spirits, employing new production processes, and having a large diversity of products in their inventory. So with these types of companies and in these processes, haze and UFO sightings are occurring more frequently, and traditional identification techniques only provide part of the story. So how do producers address these quality issues? Microscopy, and we'll be talking about microscopy today, is a tried and true methodology for observing and, in some cases, identifying the source of these quality products, these contamination issues. Today, we're going to be talking about coupling spectroscopy with microscopy. So you have two methodologies that are integrated together that can bring a fuller characterization of the problem. Infrared spectroscopy is used in the food and beverage industry in other applications besides contamination identification. Near-infrared spectroscopy is a common technique used in process control or process monitoring, raw material qualification, product mixing, and we're typically looking at water, protein, and carbohydrate concentrations using this methodology, not exclusively, but it's very commonly used in qualifying grain products. Mid-infrared spectroscopy is used in reaction monitoring. There's a trans fat method based on mid-infrared technology, trans fat quantification method. We also can quantify protein, fat, and carbohydrate concentration. And there are dedicated dairy and wine analyzers which are based on mid-infrared spectroscopy. And that's the technology that we'll be speaking more in more detail about today. Another type of spectroscopy is accomplished not with infrared spectrometers, but with filter photometers. And these are more dedicated process analyzers for single component material quantification, including sugar in carbonated beverages or ethyl alcohol in beverages. Other scientific instrumentation techniques include chromatography, gas chromatography, coupled with mass spectrometry. This technology can provide trace level determination of contaminants, and this technology would be used to address the pesticide issues. If you have small quantities of pesticides on food products, you would need to use this type of technology to detect it. And then various different atomic spectroscopy methods, including X-ray methods, are used to detect metal contaminants. So a little bit of an introduction to infrared spectroscopy and what it is. So infrared spectroscopy is a vibrational spectroscopy. So I'm going to use my mouse to point things out on the slides. In infrared spectroscopy, we observe absorption bands, and this is the absorption spectrum of water that I'm showing in the upper right-hand corner. We can plot spectra in absorbance with the peaks going up, or in transmittance with the peaks going down. Infrared spectroscopists, to complicate matters for everyone, tend to show them either way. They are mathematically convertible between one another, and it really doesn't matter which way you observe them. But I think in our presentation, we're showing all the spectra in absorbance. That's just a kind of a detail. But the bands that we observe are due to the absorption of infrared radiation, which causes the molecule to vibrate with increased amplitude. So in the case of water, we observe a band, and this is where infrared light is being absorbed due to the OH stretching mode, and this is observed around 3,400 wave numbers. And there is a corresponding bending mode that is observed at about 1640 wave numbers. Water is a very simple molecule having 3 atoms, so it has a relatively simple infrared spectrum. Most organic molecules are relatively larger, and you see a more rich spectrum, as is shown on the bottom, for polypropylene. So this is a polymer spectrum of polypropylene, a relatively complex molecule, and you'll see many more absorption bands, these peaks pointing upwards. So these spectra can be used as molecular fingerprints, and two different molecules with different molecular structures will have unique infrared spectra. So we can utilize these spectra as fingerprints to identify unknowns. And the way that we do that is on the computer, we store spectra of known materials, qualified materials, and then we can do digital comparisons using the computer against this library to identify unknowns using the same type of methodology that forensic scientists use to try to find suspects based on fingerprints. So the way that the process works is we have an unknown material. We have an infrared spectrometer which illuminates our sample with infrared lights, which we can separate by frequency or wavelength. Then we search that spectrum of the unknown against a library, and then we're able to identify the contaminant as polypropylene in this case. So most of the, or virtually all of the spectrometers these days that are used in unknown identification are what we call Fourier transform infrared spectrometers. These types of spectrometers allow for very rapid data collection, and because of the sensitivity and speed of these systems, many different optical accessories have been developed to handle many different applications, and that would include liquid and gas vapor cells, attenuated total reflection, which is a contact measurement technique, and a microanalysis, which we'll be talking about today. These accessories make the job of the analyst easy, and in this modern age, these accessories and the spectrometers are very, very cost effective. So our focus today will be on infrared microspectroscopy. And in microspectroscopy, we couple imaging, visible imaging, microscopy with spectroscopy. So we can observe a contaminant. We can isolate that contaminant in terms of our optical beam used to probe the sample, and we can measure spectra of micro samples that then we can identify using the technique that I showed on the previous slide. So we'll be able to save images. This is a fully digital system using a megapixel camera. We're able to store those images on the computer and relate them to the identification that we make using the infrared spectroscopy. And virtually everything that you use in the production of beverages has an observable infrared spectrum. So, we show that on this slide for water, ethanol, yeast, and ground corn. So the only types of materials that don't give rise to an infrared spectrum are things like purely ionic materials like sodium chloride, common table salt, or homonuclear diatomics like nitrogen, oxygen, hydrogen, those kinds of things. Everything else has an observable infrared spectrum. So this is the system that we use to solve the problems that we'll demonstrate just a little bit later. It's called SurveyIR, and SurveyIR is an infrared microspectroscopy accessory that interfaces to virtually any FTIR spectrometer. The data that we're showing today was recorded using the system shown on the right, the Curie 630 FTIR spectrometer on the right part of the picture, and the Czitek SurveyIR microanalysis accessory, which is shown on the left. The SurveyIR is a sample compartment mounted user-installed accessory. It's very compact. It is very reproducible in its mounting, and there's no user alignment required. All of the power is provided through a single USB connection, and incorporated with SurveyIR is an attenuated total reflection ATR element. It's a diamond ATR element, and we'll talk a little bit about that later. No liquid nitrogen is required with SurveyIR. It uses the instrument's own detector, and it's very compact and can even be transported if you require to bring the analysis technique to the location of the problem. And it's a very affordable microspectroscopy solution as well. So as I mentioned earlier, SurveyIR couples microscopy with infrared spectroscopy. So these are all images that we recorded on materials which are relevant to food and beverages. But we have very excellent image quality, and we have incorporated an illumination technique in the system called oblique illumination. And the three images moving from the left to the right are all observed under oblique illumination, which is also called dark field illumination. And this works extremely well with most samples, and we get very good quality images from the system. The other thing we have incorporated, and time does not allow us to talk about this in great detail, is a view-through attenuated total reflection device incorporated with SurveyIR. So attenuated total reflection, ATR, is a contact technique where we measure the material by contacting it with a diamond crystal. And this is an image of a material of blue impurity, which is shown on the left-hand side. The image on the left is viewed through the diamond. The image on the right is the specimen in contact with the diamond. So with this technique, it minimizes sample preparation. All you need to do is contact the sample with the diamond to measure it, and we can also visualize and verify contact during the analysis. So at this point, I'd like to hand over the presentation to Dr. Spedding for a few slides, and he'll tell us more about the problem of contamination in beverages.
Okay, so yeah, getting back to UFOs, which Dave pointed out is a term that we came up with in response to quite a number of questions we get from our brewing and distilling clients. Wanted to just give a brief overview of what we're looking at, and then we'll get to some exciting examples that we've been resolving through the FTI spectroscopy studies with Czitek labs and quantum analytics. But haze is, as you see there, essentially a result of light scattering by colloidal or larger particles suspended in a solution. They're kind of gel-like in appearance, and the brewers have given them some interesting terms over the years. The picture you see there of the glass of beer, brightly lit, shows you that essentially that light scattering. And this is known as a snow globe effect. When a beer presents in such a fashion, it's known as a snow globe. We have some elegant terms such as elephant snot and other delightful terms that describe some of these unsightly, unappealing components. We, as an analytical lab, and most brewers and distillers with some basic equipment can make some general observations about what is causing the haze, but most of the time, I'd say 90% of the time, we get stumped with a question. Hence the term UFO, unidentified floating objects. In general, as you see with the chart here, we're looking at, for beer and distilled spirits, you're looking at copper and polyphenol content from any grain-related material, and of course with distillers particularly using copper stills, copper ions and polyphenols can be a problem. As brewers know, one of the big issues is with protein and polyphenol haze, chill hazes, which can be permanent and temporary. Brewers have kind of generally resolved those, and we can answer those questions fairly quickly. It's some of the unusual things that crop up that we have a problem with. Those other concerns that we can address are sometimes mineral related, particularly for distillers using non-mineral free water for dilution, and also brewers having issues with calcium deposit buildup in which we call beer stone. So minerals account for about 20% of the kind of problems that we see. Iron specifically is a big problem for both brewers and distillers, excruciatingly so for distillers of bourbon production. Polysaccharides, carbohydrate material from grain husks, from other vegetal sources can be a problem of hazes. And we'll see a couple of examples of this come up from the Czitek group shortly as Dave gets back into discussing the technologies that they use. Microorganisms, as he mentioned, are visible within their techniques and technologies and under light microscopy, but are not of a concern for us today. We'll actually identify those by other means. And then we come around to fatty acids and fatty acid esters. And this is something that you're going to see a couple of examples of in a moment that is a particularly acute problem right now with distillers. A couple of examples will follow when Dave comes back on. Let me move to, Dave, can you move to the next slide? It doesn't look as though I have the control. Next slide, please. Oh, there we go. Okay. What I normally look for and what some brewers look for under light microscopy are traditional materials that Dave mentioned are naturally present in beer and beverages and not necessarily a big concern for us. So we look for protein, and protein appears in the form of skins, strings, and flakes. And you see one marked on the stout slide to the right of the slide there, a normal protein. They look like very delicate, fluffy kind of skins, lacy materials. These are normal unless people are doing a really tight filtration, in which case we get essentially what I call gritty protein. These are differentially stained, in this particular case with eosin Y. It's a yellowish stain that stains protein distinctly pink to red, depending upon the concentration. This gives us some indication if we've got a protein polyphenol problem. We also see here another issue excruciatingly common for beer producers, and those are oxalate crystals. When we move on to another slide, I'll show you some better examples of oxalate crystals. But these are the 2 or 3 kind of things that I can detect under light microscopy. And the brewer with a small centrifuge and a decent microscope and some differential dyes can stain protein, they can stain carbohydrate material, but that doesn't really get us very far in terms of a full analysis of what we're looking for. So we do need to move on to something a little bit more involved. Let me see, next slide, please. Just a quick review of oxalate crystals again before we move on to something more substantial. Here's a typical example in beer of oxalate crystals, and you will note that they kind of reflect light or refract light a little bit to form what's called Maltese crosses. We also see some kind of semi-barrel shaped crystals that may be sulfate crystals, but the main crystals in the image under the beer heading are oxalates, calcium oxalates, very common in beer stone and beer stone buildup, and also if there's an inadequate amount of calcium in the beer production early on. In spirits, they tend to form what they call rapide crystals, needle-like crystals. So if I find these under the light microscope, I can usually address the problem. It's when we get beyond this that we have some problems. Next slide, please. So where are the limitations for identification? Or not, as the case may be. The traditional limitations for us are that the total amount of particulates is very, very small. We're talking about 3 to 10 milligrams per liter of samples. So unless you can centrifuge those down and get a good microscopic view of them, they're a little bit difficult to handle to begin with. With distilled spirits, you see a single piece of flock in the picture in this slide. These go back very readily into solution on occasion. So colloids can go back into solution, and then it takes a little while for them to appear out again. So sometimes it's very difficult and very time consuming, waiting over a period of weeks to figure out if you can get enough material to actually do a basic identification. Again, centrifugation and some of the techniques that they use in FTI, IR microspectroscopy can be a little bit more advantageous than looking under a regular microscope. So, so as I mentioned earlier, if oxalate crystals aren't seen and the protein characteristics and qualities are not as I expect them to be, or I don't detect carbohydrate or do detect carbohydrate, then we really are kind of limited in what is causing the problem, both for brewers and for distillers, and then usually means going back to other more extensive tests. If we can get a quicker identification, that would be ideal. And it looks like by FTIR microspectroscopy that Dave will talk about again in a moment. If you can see it, the SurveyIR can analyze it. Single particles can be used for identification. You can take a picture of it to see essentially what it looks like under the general microscopy conditions, and then with their library technologies, they can go back in and look at particular identities of these UFOs. So that's kind of an interesting technology that's coming up. We have submitted some samples and they have had some analysis of samples going on. So I'll hand it back over to Dave and he can tell you some of the exciting findings that we've seen with respect to beer and spirits.
Thank you very much, Dr. Spedding. So the first example that we're going to talk about is a particulate contamination in beer, and these are actually several different examples from beer. And on the left-hand side are photo micrographs, video micrographs recorded on SurveyIR of the 3 different contaminants, whose spectra are displayed on the right side of the panel. So in the upper left image here of a twisted fiber, we observe the spectrum that you see on the red, which is most closely associated with cellulose. Cellulose is an extremely common contaminant, not only in spirits, but in many, many different products due to the ubiquitous nature of cellulose, plant-based fiber. In the middle, in the green, is the infrared spectrum of a white flake, which is displayed here on the right image. And this is the signature that one would typically observe for a protein, and infrared spectrum, because of the complexity of proteins, they're very large molecular weight molecules, we can readily identify the contaminant as protein, but we can't take it very much further than that. We can't say that it's protein from wool, or is it animal-based protein necessarily. This is not protein from wool, because wool, its image would be of a fiber, and wool fibers have relatively specific habits, images, which coupled with the spectra allow you to say, well, that's an infrared spectrum of wool, and that's what a wool fiber looks like. I'm sorry, that's an infrared spectrum of protein, and this is what a wool fiber looks like, so this must be a wool fiber. In this case, we can't take it any further than to say it's a protein with this image that we've observed here. And then the last example is this white UFO, which was identified as polystyrene. Polystyrene is very common as well. Your coffee cups from Dunkin' Donuts or elsewhere are polystyrene styrofoam cups, and this material is also used as packing material and can get into products in very circuitous ways. Microplastics is a huge environmental problem and has been observed in a bottled water and other beverage products, and is a very well-reported contamination and very ubiquitous contamination, which infrared spectroscopy can readily identify. This is a visible haze in beer, and in this case we took some material from the beer and dried it on an infrared substrate. We're able to record a spectrum directly from that, which is consistent with a polysaccharide material. The spectrum is similar in appearance to corn syrup, even though it is dried. Because of the nature of polysaccharides, it retains water, so we also see a water signature in here. This peak at 1640 is typical water absorption band. Another example of micro haze or visible haze in beer. Once again, some material dried on a substrate. We observe these microspheres, and the spectra of these spheres were consistent with a polysaccharide as well. It's a very close match to hydroxypropyl beta cyclodextrins, and we note via the attached reference that natural cyclodextrins have the ability to form larger aggregates as microspheres when concentrated, and will exhibit poor solubility in aqueous solutions, so they'll drop out of aqueous solutions. The next example is an example of particulate contamination in aged whiskey. And on the left-hand side, we have seen this image in the past. This is an image of a particulate that is filtered from the whiskey, observed under oblique dark field illumination in SurveyIR, and we're actually viewing through the diamond crystal, which is utilized for the attenuated total reflectance measurement. So this contaminant shown in the red was recorded by contact just by touching that diamond crystal to to the contaminant. The identification of this material was consistent with tannic acid, whose spectrum you see on the in the middle, and a cellulosic holocellulose from oak. Both of these signals are observed in the contaminant, and the most likely source of this contaminant would be a fragment of the charred barrel, and you can further confirm this identification by taking a piece of the charred barrel and measuring it separately and comparing the particulate contaminant with the known extracted fragment from the charred barrel. This is a visible contaminant from a bottle of mezcal, which is a spirit originally from Mexico. And the image that you see on the left-hand side, again, was recorded through the diamond crystal on the ATR element interface. And we observed beautiful blue crystals. We observed, you've seen some other images of these blue crystals elsewhere in the presentation. We recorded the spectrum using contact with the crystal, shown in the red on this slide. And you have a very good correlation with magnesium stearate. Stearic acid is a long chain, naturally occurring fatty acid that's a biological chemical and is used in soaps. So we believe that based on the blue color of this material, that it was a copper fatty acid ester, and another very close match was copper laurate as well. So we believe that this contaminant originated from a fatty acid ester molecule which interacted with other material in the liquid. As we take the analysis to the next step, we got some bottles from the manufacturer that had not been filled with the spirit, and performed a hexane extraction just by putting hexane in the bottle, swizzing it around, taking some of that hexane extract and dried it on an infrared substrate. We're able to observe the spectrum on the top, which is a typical spectrum corresponding to a vegetable-based fatty acid ester. On the bottom, we're showing you a spectrum of olive oil for comparison. The material, we could not identify it as a specific fatty acid ester, but are very confident that it is a vegetable-based oil. Then we discussed our results with the bottle manufacturer, and as it turns out, the bottle manufacturer applies an anti-scratch coating to the outside of the bottles, and it was proposed that some of this coating made its way into the bottles themselves. The coating material is an emulsified wax, which was not identified, the nature of the wax, and polypropylene. We did not see any polypropylene in our analysis of these bottles, but numerous waxes were among the spectral library correlations, and we're very confident, as we said before, that this is a vegetable-based oil fatty acid derivative that somehow reacted with copper cation somewhere in the process to give rise to this salt, the copper salt. So, in conclusion, the increasing number of new spirits and brews and new approaches to their creation are leading to a plethora of new haze and unidentified floating object contaminants. Current methods of addressing these haze UFO issues can be time-consuming, tedious, and in some cases not specific enough. And careful brewing and distillation processes can help resolve some of the haze issues, but these treatments will not address all issues, and nor are older methods of analysis always successful at identification. The new FTIR microspectroscopy tools can expose important details on these UFO and haze issues, and the SurveyIR microanalysis accessory can provide the necessary details without the typical burden associated with FTIR microspectroscopy methods. And so at this point, I'm going to turn it over to Brian DeVerse, and he will bring us to the end of the presentation.
Excellent. Yes. Wow. Thanks, Dave and Gary, so much for that. This has been an awesome presentation. And it does look like we have a few questions here. So if you could advance the next slide. Yeah, that's right. Okay, question and answers. This is good. So we have the first question here. What if the sample can't be identified by a database search?
That's a great question. So there are commercial databases, many of them, that you can buy that are specific to industries or chemical classes or products. However, in my experience, the best results that can be obtained with library searching methods is a mixture of commercial databases and homegrown databases. So within your industry, within your products, you have various components that are used in the manufacture of the products, or are used in packaging the product, or somewhere else in the process, maybe not even specifically intended to appear in the product. Say lubricants used on automation methods. And so where I'm driving at here is in your free time that you develop your own library of known materials that are in your plant, in your factory, because those are the most likely things to lead to contamination. And if you go through a successful analysis and are confident that you've identified a contaminant, you also can add that to the library. So these libraries can be user-generated, user-edited, and I think the best results are when you develop at least some of your own libraries based on the materials that you encounter on a daily basis, either in the manufacture or the processing of your product.
Excellent. All right, so here's another question. Your presentation showed various modes of data collection, like ATR and transmission. Do you
Yes.
have recommendations as to which IR collection mode you should choose for your analysis?
It depends on the sample. I think that ATR is the preferred method if you can employ it. And what I mean by that is not all samples are amenable to ATR analysis, particularly small samples, let's say below 100 microns, are a little bit too small for ATR analysis. But I think that the broad majority of samples are amenable to ATR, even if you have to remove the sample from a substrate and place it on a low E glass slide, which is an infrared substrate. The films that we showed, where you take a material and dry it on a surface, an extract, those are not typically amenable to ATR analysis because of contact. So in ATR, you need just a little bit of thickness to the sample to make good contact with the ATR element. So those examples of those dried films, doing it by reflection absorption, in other words, we reflect off the low E-glass slide through that film, will give the better results for those kinds of samples. And some of this is gaining experience. Some of it is receiving training, having some people show you, and some of it is trial and error. But I don't want to come across as these techniques being difficult. They're not difficult, but you might have to be shown from someone how to do it. I don't think it's more difficult, say, than some of the techniques you had to perform in a high school biology or college biology class, that sort of thing.
Excellent. This question here, this was from the slides. The needle-like oxalate crystals formed in spirits. Can you elaborate on what they are and how they are formed and how to prevent them?
I think that's a question for Dr. Spedding.
Yes, it's an interesting issue. I've done a little bit of research into oxalate crystals above and beyond beer. One of the things that you have to appreciate is each different distilled spirit, and this is obviously where we see the Rafid type crystals. Rafid crystals are actually found, in many food sources, many food materials. Agave, for example, has quite a high abundance of oxalate crystals. Rhubarb, if you're into rhubarb pie, rhubarb has a lot of oxalate present. So a lot of plant materials do have oxalates present. So that's the origin of them. The fascinating thing is, why do they appear in beer environment as those Maltese crosses, whereas they appear like needle-like structures in distilled spirits? Could be a function of the alcohol concentration, but there are many sources of oxalates within the biological materials that are used in beer and beverages, beer and spirit beverages.
Excellent. Here's a question. Do you need to use 200 proof ethanol or water as your reference or background so it does not interfere with your search match database?
The answer to that is no. First of all, when you run samples using ATR spectroscopy, first of all, I'm answering the question in the context of microspectroscopy. If you're actually doing solution spectroscopy, so you're using a fixed path length cell and you're actually looking at the materials in solution, let's say by transmission, then yes, collecting a background through that cell of pure water or ethanol, whatever your solvent matrix is a perfectly good thing to do. But in the context of microspectroscopy, I mentioned that those dried films had water present. They were dried, but the water is bound to the carbohydrate. The carbohydrate, the polysaccharide, has a tremendous number of hydroxyl OH groups, which hydrogen bond to the water, and it's unless you really probably aggressively heat it, which could degrade your sample, you're not going to remove those waters just at ambient temperature. So in that case, we wouldn't collect a background through the solvent matrix. We would just have to live with the fact that these materials have bound water. So sucrose, if you take sucrose and put it in water, but then put a drop of the water on an infrared window and go away for the night and come back the next day, you'll have a dried film, as it were, of sucrose, but that sucrose will have bound water and its spectrum will be different than sucrose crystals that you get out of a little sugar packet due to the bound water. And it's just the nature of those polysaccharide materials that they will bind water when they're coming out of solution. But I wouldn't record a background spectrum through water or through an ethanol containing water solution.
Okay, good. Here's a question: how can you identify a mixture sample?
That's a great question too. There are two basic ways to identify a mixture sample using spectral library search methods. Some companies have automated mixture analysis software that's incorporated in their library search. So the mixture is resolved based on the known materials which are in your library. And the second method is not automated. It is more manual, but it is still using your infrared database. And that is that when you do a spectral search on an unknown, which is a mixture, then typically the component with the highest concentration in the mixture is high on the match list. It's important also to overlay your unknown spectrum with your library spectra and make sure that you have overlap, correspondence of the signature of your unknown with your library spectrum. Then within that software, you can digitally subtract out the component at the highest concentration. So you remove it from the spectral signature by a subtraction. Then you search the residual and try to identify the second component, and you can continue that process. However, the other methodology of looking at suspects within your process is very useful in terms of mixture analysis. Infrared spectroscopy is a Beer's law method, like it's optical spectroscopy. So it obeys Beer's law, which in this context tells you that the observed spectrum of your mixture will be a linear combination of the component spectra, which allows us to use these spectral searching subtraction techniques to spectrally strip components to try to identify multiple components. And although we couldn't show that process, during the presentation, but some of those materials that we showed with multiple components, this was the methodology that we used to aid the identification.
Okay. Well, that's about all the time we have for today. Thanks again to our presenters, Dave and Gary, for today's very informative discussion and your presentation. And thanks to everyone that has joined us today and for all your interesting questions. I hope you found this session worthwhile. If we didn't manage to answer your questions, there's no need to worry. We've collected all your questions and we'll respond to your questions directly by email. If you would like to listen again to today's webinar or invite a friend to listen, it will be available to watch on demand in a few days' time. So don't forget to visit our resource page on lqa.com. This is your resource for application notes, technical papers, and some past webinar recordings. And please stay tuned to our soon to launch summer webinar series starting this June. So again, thanks to everyone and goodbye.